welcome back. It's a pleasure to say that we are starting the lecture by Matt Stoffregen, who will give us a tour over monopole Floer Spectra.
Yeah, great. Yeah, thanks. Thanks to the organizers for putting this together, and also thanks for the opportunity to be here. It's great to be in town. So this is a sequence of talks about monopole Floer spectra, and what is the purpose of these talks? So we're going to want to associate to a three-manifold. So throughout Y will usually be a closed oriented three-manifold, and it'll usually have a spin-C structure. And the object of interest is going to be some gadget, SWF, of Y and the spin-C structure, which is some kind of spectrum. And, I'm never sure to what extent, everyone is an algebraic topologist, is a geometric topologist, it's unclear. So, to some people, spectra are just what you wake up in the morning to, and for other people, they never encounter spectra. But this object will be an S1 equivariant spectrum. And if you're not an algebraic topologist, and you're a more appropriate kind of topologist, you can just think of a spectrum as a space up to stabilization and leave it at that for the most part. This space is supposed to record somehow the information contained in Seiberg-Witten theory applied to that three-manifold. So the Seiberg-Witten equations on Y are somehow going to be used to, we'll somehow take the solutions of those equations and assemble them together into this space or spectrum or whatever you want to call it, using some fancy technology. But there's also a more standard way to take information from the Seiberg-Witten equations on a three-manifold and assemble it into some object. So maybe, somewhat more familiar is something called the monopole Floer homology of Y. Kronheimer and Mravka defined some groups HMY, Y of S, and ideally these would be closely related to each other. So maybe it's just motivation for what we'll do. I'll state a conjecture in case you're familiar with one side or the other. So conjecturally, the homology of SWF should always agree with monopole Floer homology. And in many cases, this is known, but it would be nice to have it all the way through. All right. This will be what we're interested in, but to quote Monty Python, now it's time for something completely different. So in order to get at this three-manifold invariant, it's probably a lot easier to start with talking about the four-manifold case. So for today, the plan is to just introduce. We'll just introduce the four-dimensional Seiberg-Witten equations. And this is for a particular purpose. So this monopole Floer spectrum that we want to talk about, it's kind of easy to give a lecture series about the monopole Floer spectrum because no one's ever done anything with it. So there's not too many applications you have to talk about. But it has a cousin, which is an invariant for four manifolds. So much as for three-dimensional manifolds, there's a spectrum version and there's a homology version. For four manifolds, there's something similar. So there's what you could call a homological invariant of four manifolds. So if you have a smooth four-manifold, you could count solutions of the Seiberg-Witten equations on it, and that would be some kind of invariant that sort of arises just from homology. So this is X of four-manifold. But you could also record something a little bit more refined called the Bauer-Ferrada invariant. So instead of having the Seiberg-Witten invariant of your four-manifold, you can take something called the Bauer-Frude invariant. And you could ask, if the Seiberg-Witten invariant of a four-manifold is a number, how do you lift it to something more informative? But in the first talk, I guess we have the story of categorification, which has you go up to like higher categories, starting at something mundane. But here, instead of living in a whole higher category, the Bauer-Frude invariant will just live in a stable homotopy group. So this will live in the homotopy groups of some space. So in some kind of stable homotopy group, which we'll define later. And there's some kind of Hurewicz map from this homotopy group down to the integers to recover the Seiberg-Witten invariant. All right, so that was all to say, maybe there aren't so many applications of the three-manifold invariant, but its spectral cousin in four-dimensional topology is actually pretty useful, and it has a cool application called the 10/8 theorem, which is still kind of the highlight of, is really the highlight of using Floer Spectra in low-dimensional topology at the moment. So, yeah, the plan for at least the day is I feel like we have to write down what the Seiberg-Witten equations are in order to say that we really talked about them. But for what we'll do subsequently, we don't need the equations themselves. We only need a couple of technical properties about them. And in the last two lectures, we'll just use those technical properties to discuss both the three-manifold invariant and actually prove this 10/8 theorem. So, yeah. Any questions before we talk a little bit about the Seiberg-Witten equations? Cool. And also, does everyone already know them? I feel a little bit bad. We're gonna go and just set up all the definitions to do them. Hopefully that's okay. Yeah, I'll take that as a yes. Great. I mean, we're gonna go into a little bit the no man's land of if you already know what this topic is, then it's looking at it again, it's really boring. But if you don't know what it is, you can't. It's still really boring. But if you don't know what it is, it might. It's usually too fast to make any sense of. But at least we can get part of it. And I think one thing that if you do think about the Seiberg-Witten equations, usually not everyone who does that knows where the pin-2 symmetry comes from. So we can at least try here to say a little bit about where the pin-2 symmetry in the Seiberg-Witten equations comes from. And occasionally that's quite useful. All right. Good. So let's start first things first. Let's say you have a closed four-manifold, oriented. And we're going to say it comes equipped with a spin structure. And then we think realistically, and then we ask ourselves, do we really know what a spin structure is? And then we write it on the board. So what does it mean for X to have a spin structure? Well, okay, in the beginning you have your four-manifold, and it comes to its nice smooth four-manifold, and associated to it you have a tangent bundle. But you could think of the tangent bundle, instead of being a tangent bundle, as being the bundle of frames over your four-manifold. So that means that the frame bundle is the set of maps from R4 to the tangent bundle of your four-manifold. So where a frame, so that means a frame of Tx together with a point in the base. But of course, this is a principal bundle with fiber SO4. So, any two frames of the tangent space at a point are related by a change of, by just a linear transformation. But SO4 is a reasonable group. Right? Pi 1 of SO4 is E mod 2. And so it has a double cover called spin 4. And spin 4 is, in particular, spin 4 is simply connected. But spin 4 is special among all the spin groups in that it actually decomposes as a product. So spin 4 is SU2 times SU2. which is one of the famous exceptional isomorphisms for Lie groups. So this isn't really an obvious, this isn't an obvious claim at all, but you can prove it using quaternions, which we'll do in a second, actually. Great. So yeah, SU2 times SU2 is a double cover of SO4. And the four-manifold is spin if you can find some lift of the frame bundle to kind of a set of spin frames. So this diagram requires that you find some spin 4 principal bundle so that at each fiber downstairs you have a copy of spin 4 lying over the SO4 in this one by the usual double cover. Now that kind of description is really annoying because what does that even mean? But maybe we can rephrase it to make it more convenient. And the way we'll rephrase it is in terms of the associated bundle construction. So if you're into gauge theory, you do associated bundles all the time, but otherwise, maybe not so much. So yeah, let's have a very general situation. Let's say you have a group G. Unfortunately, the group lost all of its vowels, but we'll look at that. You have a representation of G acting on a vector space V. And let's say you also have a principal bundle. So a principal bundle meaning just a fiber bundle with fiber G. But you can somehow use the information of that principal bundle together with the representation to turn it into a vector bundle. So in particular, you could take the product of P and of the principal bundle P and the vector space V, and you could mod out by this relation. So you could just say, we take the product and we mod out by, you're allowed to slide the variable around. So you're just modding out by the G action on the product. And you can see that this actually fibers over the base X again, and now its fibers are a copy of V. That still might feel pretty abstractified and not extremely concrete, except that we already have a good example of doing this in practice. So as an example, let's, still using the notation of X for our manifold, the tangent bundle of X is actually the associated bundle of the frame bundle. So if we take the bundle of frames as before, so that's some SO4 bundle. And we did the associated bundle construction on SO4 together with its standard representation. Then we just get back the tangent bundle. So, you know, at least in this one case, it's not, what this construction is doing is not so mysterious. It just says that you can go back and forth between principal bundles and vector bundles to some extent. Right, but using what's on the board here, we could say, instead of building associated bundles with SO4 representations, all of a sudden we can build vector bundles using spin 4 representations. Yeah, it takes a long time to actually write down the equations, but I figured we had to do that. You know, it's some kind of moral imperative. Right, but let's look at some nice associated bundles. So let's find some spin 4 representations, and then we'll turn them into bundles. So let's first consider two things, H plus and H minus. So the H stands for quaternions, and we'll define spin 4 actions on them the following way. So in H plus, the action of a pair elements of SU2. So this is an element of spin. Is this going to act by the second variable? And in the second copy, the spin group acts by just the first variable. So you can think of spin 4 as being, you have two copies, one of which is labeled plus and one is labeled minus. Right, so you have access to these two representations. Those don't look, they don't look so interesting. But you also have access to another representation. What else can we cook up with using spin 4? Well, we could try to act with both variables at the same time on quaternions. So let's write H minus and plus for where you act by minus on the left and plus on the right. So in this representation, if you take a quaternion V and you want to act by spin on it, you act with the minus spin on the left and then with the positive thing acting on the right. And you have to take the inverse in order to make it an actual group action. Right. But this representation is actually already pretty familiar. So for example, we could take -1, -1 and apply it to V, and what should we get out if we do -1, -1 on V? It should return, right, if you take the -1 as an element of SU2, both of these are really just the unit quaternions -1, so it returns to itself. So this representation of spin 4 actually has one of the elements of spin 4 is not acting at all. And in particular, this is the center of spin 4. So this is a representation of spin 4 modulo its center. And that quotient is exactly SO4. So whatever this new representation is, it's actually an SO4 representation. And if you stare at it for a little bit, you can actually check that it's the standard representation of SO4. All right, so now for each of these three representations, we've gotten a bundle. So for H+, we'll say we build out of it the positive spinor bundle by the associated bundle construction. And S- is the negative spinor bundle. But then this one over here is just the tangent bundle by construction. Oh, sorry. So but now we've got these two new bundles which actually look kind of interesting. They're not as sort of elementary as the tangent bundle, but they have a very similar definition. And what we're going to need to define the Seiberg-Witten equations is Clifford multiplication. But when you do everything in terms of representations, this becomes maybe clearer than it is in some other ways. So for us, this will just be an observation. That there's a map of representations So let's say you take the SO4 representation here and the positive spin 4 representation there. There's a map of representations from this to the negative representation. And let's see how it goes. So it's not so bad. You just take your first quaternion, your second quaternion, and then you just do quaternion multiplication for them. Not so scary. But you want to check that this is actually a map of representations. So let's act by PQ. So the action on the first term is PAQ inverse. And on the second term, it's Q phi. So yeah, once you do this multiplication, you actually do get down to where you expected. right? To act on a negative spinner, you p acting by p comma q just multiplies you by p. Rather. So that doesn't seem terrifically interesting, but the associated bundle construction is actually a functor. Like if you have a map between representations, you get a map between bundles. So what we've just constructed there is actually a map from S plus tensor tangent bundle to S minus. But yeah, I mean, so these are two, it's hard to really get your hands on what a spinner is. Right? And sections of these two bundles are called spinners. It's hard to really visualize what they're doing, but at least from this point of view, we've constructed a map like this, and this will be called Clifford multiplication. All right. Yeah, any questions at the moment before more representations? Right, well, I mentioned at the beginning that the Seiberg-Witten equations are supposed to come with a pin 2's worth of symmetry. Or naturally they come with an S1 action, and you can see the S1 action in this setting, looking at the right action by the circle on spinners. So we've been defining representations from the left, but that means you have a residual S1 action on each of these terms, or on at least the first two terms, by acting on the right by the circle. And it turns out the Seiberg-Witten equations are going to take as input a spinner, and that circle action on the right is going to give you an action by a whole gauge group with an S1 symmetry. So you have the constant loops, which are particularly good, but you also have any map from your space to S1 acting on the right as well. But the pin 2 action is only visible in this sort of way as constant maps. It's not some kind of further infinite dimensional gauge group on top of the ordinary one. So in order to find the pin 2 action on spinners here, it's not so complicated. We'll just maybe define it over here. So now we're going to act by spin 4 cross pin 2, where pin 2 is going to be a subgroup of spin 4, in effect. So this is going to be a triples of points, PQ are in SU2 and R's in pin 2. And I should say that pin 2 sits inside the unit quaternions. So it's a copy of the unit circle in C, along with one of the other quaternions times the unit circle. Right, and we'll see why you need the funny definition as time goes on. So here the action now it sends a single vector to the same thing as before. The positive spin acts on the left. But now the elements of pin act on the right. And R doesn't do anything in the third presentation. But yeah, in fact, I mean, you could say even more. The spinners are going to have a right action by the quaternions, and you'll have lots of symmetry. But it turns out that only the pin 2 symmetry will survive to the equations at the end. All right, but to go further, we need to not only define the Clifford multiplication, but just say briefly what the Dirac operator is. So in order to do that, let's write a theorem. The dreaded theorem / definition, the worst kind of statement, but we'll do a theorem / definition. So a connection so let's say we have a connection on the spinner bundle. So it's going to take positive spinners and spit out negative spinners together with a cotangent vector. So, you know, if you don't think about connections, usually you're just supposed to read this as saying a connection is something like a derivative, right? If you take a derivative of a function on Rn, you have to record in what direction you're taking the derivative. That's the cotangent bundle factor. And then you record what the derivative actually is in that direction. That's the second part. So delta is something like a derivative, but because you don't have preferred coordinates, there may be many choices of connection in the world. There's not, you know, there's many connections, and that, in some sense, that's what gauge theory is about. But for spinners, there's a preferred connection. So a connection is spin. So if you're on the spinner bundle, you can talk about spin connections. A connection is spin if that Clifford multiplication map we defined over here, the Clifford multiplication is parallel. Which means that the connection applied to Clifford multiplication is 0. And the theorem part of the statement is that there's a unique spin connection. So once we've identified, you know, we aren't going to write down what the spin connection is, but suffice it to say it's, you know, the analog of the Levi-Civita connection for spin manifolds. It's just a lift of that one stage further. We don't have to say what it is, but it's good to know that it exists. It gives us some way of talking about differentiation that really is independent of coordinates or any other choices. Right, and that's really the key ingredient to the Seiberg-Witten equations. This, the fact that we have a connection going one way, and we also have Clifford multiplication that goes backwards. Sorry, this should have been a plus. That's a terrible situation. So you can increase the size of your spinner, and then you can smush it back down. All right, so define the Dirac operator applied to a spinner is just you take the spin connection applied to it, and then you apply Clifford multiplication. And the result is going to be a negative spinner. All right, and we need just one other geometric ingredient to.
Sorry.
Yeah, go for it.
The multiplication goes from the tangent bundle.
Good catch. Tacitly, we're going to identify the tangent and cotangent bundles by the metric and never make any reference to it. So, good, yeah, thanks. I actually made a mental note to address that. Okay, one further piece of geometry, and in fact, the thing that seems to, I don't know, this is something that's special to dimension 4, and it seems to be the main thing. Let's say you take the bundle of two forms. The bundle of two forms, and I mean, in any dimension divisible by 4, is going to have the Hodge star. Well, the Hodge star will preserve it, but also the Hodge star squared is the identity. So you can split it into eigenspaces, and it turns out they're both dimension 3. Right? The space of two forms is a 6-dimensional bundle over your 4 manifold, and the positive and negative eigenspaces turn out to have the same dimensions. And for what follows, let's just say that we'll define pi plus to mean projection onto the plus part. So if you take a 2 form, you can just project onto the plus part using the L2 metric. Or not just L2, but you You can even do it fiberwise. All right. So now, for us, the Seiberg-Witten equations are going to be as follows. You're going to take two inputs. So our first input is going to be an imaginary valued one form. So the I, unfortunately, the I is important to making everything work out, but for the most part, you can just ignore it. Together with a spinner, as advertised. Well, we only have a few things available on the board, so we should use all of them. First, we should use the Dirac operator. So let's take the Dirac operator. And there's also something called the spin-C Dirac operator, which is what we're using in the background, but without saying it. So we're going to apply, instead of defining it, we can just write it like this. You take your one form, and you do Clifford multiplication of it to phi. And the first part of the Seiberg-Witten equations will say just that we require this to be 0. Writing these down is kind of fun because you can see that there aren't a huge number of choices, right? If you just were handed a spinner and a one form, you don't have that many ways to combine them to say something interesting. And the particular choice of some things in the equations are important. Like if you change, there's a few signs that will appear, and if you change the signs, the story will not go nearly as smoothly. So, it's a miracle that these work out, but at first it doesn't seem unreasonable that there would be something good to try because there's not that many expressions, but only one of them is truly good. Anyway, so this is the part of the equations involving the spinner. And then you have to involve the curvature of the one form, which for us, we'll just say is something maybe not too complicated. You just take d plus of a. So d plus means you take the exterior differentiation and then project it to be a positive 2 form. Then, we could use Clifford multiplication to turn that into an endomorphism of the spinner bundle. So as it stands, right, this is some omega plus element, so it's a 2 form, but we can apply Clifford multiplication multiple times to turn it into an endomorphism of the spinner bundle. And then we want to add in what looks like a truly strange expression. And we're going to multiply all of that by I. The I factor you can sort of morally ignore, but, sorry. The way I want, yeah, we have to keep the I. But you can, for the most part, ignore the I factor. All right, but what does this expression mean? This is by far the weirdest part. But you're supposed to think of this as an endomorphism of the spinner bundle. So this second equation lives in endomorphisms of the positive spinners. So namely here, phi star is a map from S plus to C, and it's the map obtained by taking your spinner and doing the dot product with phi. And then tensor phi means you just take that map to C and then you multiply by the spinner you would have gotten out at the end. The second term is there. You subtract off the second term so that this is actually a traceless endomorphism. So for formal reasons, it turns out this endomorphism is traceless. And if you subtract off the right multiple of the identity, this one will be traceless as well. So this whole expression lives in not just endomorphisms of the spinner bundle, but in traceless endomorphisms. Great. So now the goal, we have a very specific goal for today, which is to write down a few claims about this so that we never have to write down the equations again. You know, avoiding doing work is a good cause. So we'll try to extract some things which are actually important and then try to avoid going back into it. So the first thing we want to do is check that these equations are actually pin-2 equivariant. Yeah, maybe we can do that for the top one, and then for the bottom one it can be left as an exercise, but it's reasonably similar in both cases. So let's do the top. So we already said that the Dirac operator was pin-2 equivariant, so we just have to check that the multiplication is. So we can take our one form and our spinner, and this time around, after acting on it, you get, so you have PA Q inverse in the first part, and then you have Q A R inverse in the second part. Q phi. And indeed, it actually goes to where you expected it to go. So PA phi R inverse, which is the same thing as the action of P on the left is the same, and you have the right action of pin-2 on the right. So this multiplication actually respects the action of quaternions on pin-2, or on minus H. And you can do something similar downstairs. Great. So they have some kind of pin-2 symmetry. But actually there's something a little bit wrong with that calculation, which is up here that we had an imaginary one form. So we had multiplied the one form by I. But over here we were treating this as if it was like a real one form. So you have to be a little bit more careful than what was going on there, but it essentially still goes through. But yeah, in order to extract as much information from this as possible, instead of thinking of it as just equations, we want to reimagine it as a map. And this is originally due to Furuta, or this way of thinking about things. So Furuta would say that this is a map that takes as input two things, right? It takes as input a spinner and a one form. And it spits out several pieces. So it has one output, which is a spinner. Again, that's the first term. It has one output, which lives in the endomorphisms of the spinner bundle. And if you'd like to set this up to do analysis with it, there's one further thing to the equations that you would add on, a so-called gauge fixing condition. So these are the ungauged Seiberg-Witten equations, but then you can add on one more term so that you've gotten rid of almost all the symmetries. So we're going to treat that as being there as well. So you have this function on x that's also part of the output. All right, so you have a map and between these two spaces. And unfortunately, both of those spaces are gigantic, right? Each of those is some Frichet space. And they also each have an action of pin-2. And then, you could ask how to extract information from that. So originally, Witten proposed that you could just take the solutions to this. Those are the so-called monopoles. So the first invariant you can extract from such a map, or you can just count the monopoles. And in an appropriate sense, that's going to be an invariant of the map. But, you know, we can put on our topology hats and say we're topologists. We might want to extract information from this map by just taking the homotopy class of the map. But the problem in doing that, right, is that each of these are just linear spaces. That there's no, both of the input and the output are contractible. So it seems like there's no, you know, there's no homotopical invariant from this. But slightly more is true than just saying that this is a map, right? So originally Witten had shown that the preimage of 0 of this map is compact. So that's pretty special. But you can generalize this a little bit, as Furuta did. With this isn't much more complicated. But he showed that the preimage of bounded sets are bounded. So that's actually a lot stronger than the preimage of 0 being compact. It doesn't, I mean, the way I'm stating it, it doesn't imply the first one, but Furuta's argument would also cover the first one. But this says that, you know, even though these are infinite dimensional, if you take a pretty small neighborhood in the second space, that preimage is not going to be compact because the preimage space is not even locally compact, but it at least is not stretching off into infinity. So instead of looking at, you know, the homotopy class of this map, you can ask, well, what about the homotopy through maps like this? You know, that seems a little bit better. But even that is not good enough. So you can think about the homotopies that take bounded set, or that have preimages of bounded sets are bounded. So it's kind of like properness for non-locally compact spaces. And it turns out there's still no information there. But then you can look at the form of this map to see that it's got even more properties than listed. So the Seiberg-Witten map is something that you might call very compact. Maybe we'll say what that means next time, but SW map is very compact. But roughly what that says is that the Seiberg-Witten equations have an order 1 part, so they come with a differential, which is a linear differential operator. And then they come with a nonlinear part. So right, this part of the equations is completely linear in the inputs. And then you have some nonlinear part, but it's very mild. And very compactness is a way of measuring just how bad this nonlinear term is. It's not very, it's not all that restrictive actually, but you know, this part involves no derivatives and it doesn't involve anything too exotic beyond that either. And it turns out if you dig into, you know, weird old Soviet literature, I mean, I think Furuta probably figured this out independently and didn't find it in this source, but it's a theorem of Schwarz from like 61. Although it's not expressed in this terminology, this is how we'll render it here. That very compact maps of index n between two Hilbert spaces. So let's say you have two Hilbert spaces, H1 and H2. You have a very this set of very compact maps between them. Sorry, I should also assume H1 and H2 are infinite dimensional. The set of very compact maps up to homotopies of very compact maps is exactly the same thing as the stable homotopy groups of spheres. So if you take this says if, as you take your spheres very large, so let's say you want to find the set of maps of an n-dimensional sphere to a sphere of dimension n lower. If you've suspended enough times on both of them, then this will stabilize. This is the nth stable homotopy group, or the nth stable stem. So we usually call this pi n of S0. Even though it feels somewhat, silly to write, oh, we're taking the homotopy groups of S0, but you're taking the stable homotopy group of S0. So this theorem says that, even though initially you don't have a reasonable notion of homotopies between maps of infinite dimensional spaces, if the maps you consider are sufficiently good maps, they have sufficiently good analytical properties, then really you're just looking at stable homotopy. And the upshot of this, which maybe we'll restate at the beginning of next time, is that the Seiberg-Witten equations actually give you, just by having a map like this, they just spit out an element of the stable homotopy group of spheres. So maybe next time we'll say how you can use that to prove the 10/8 theorem, and also that brings up many open questions. Like you can say, what sort of maps can you get in the stable homotopy groups of spheres that actually arise this way? And there's only like 2 examples known. So it's a really sad and totally open question of what exactly is the output of this map. So if you're allowed to range over all 4 manifolds, just what kinds of maps of spheres can you get out? And indeed, essentially nothing is known at the moment. So I think that's a good place to stop for today, and let's do lunch.
We have time maybe for one quick question, since we are all past.
Okay, so suppose there is a finite group reacting on H1 and H2 in this theorem. Is then equivariant analog true?
Yeah, that's what I was, that was the next page of notes. So yeah, it's going to say that not only a finite group, but if you have any compact Lie group, the theorem remains true. So, but there's some technicality, but yeah.
Okay, so let's push the next questions to next lectures, and let's thank Matt again. We meet here again at 1:15 p.m. So 1 hour and a half, a little less.